Milton being 60 years young.
Yeah.
I think, as Nick alluded to, I'm going to talk about large-scale photonic integrated circuits, but it's really, you'll see that what this is about is high speed, and it's about integration. And because of that, you'll see that a lot of Milton's work also is intertwined with what I'm going to talk about. So what I'd like to start out with is where did this all begin? And when I say where did this all begin, I'm talking in context of the large-scale photonic integrated circuit. And I think you cannot argue that where it all began was with the transistor of Bardeen and Braden. And the list is long of how this has impacted the world. But if you look, it's everything from the discovery of the hole, the basis for the p-n junction, the basis for the integrated circuit, and the basis for the semiconductor industry as we know it today. Without the transistor, there would have not been this massive investment in the semiconductor industry. We would have not been able to figure out how to carve out all of these elements and have this manufacturing infrastructure that we have today that has generated everything from the communications revolution to really truly changing everyday life for almost every individual on the planet. And I think this was the beginning. However, I think the other key inflection point really was the discovery of the alloy laser diode. Diode laser.
That's okay, Fred. It's okay.
So, and what this did is it showed us the viability of 3-5 alloys as useful devices. And as Russ said, there isn't a 3-5 industry without the alloy, right? It's
Let me interrupt for just a second to mention something to the rest of you. We all connect back to that because that's John Bardeen, and he's the guy that brought the semiconductor here. And it would have been no basis to bring the semiconductor here if it weren't that, the transistor. We all connect back to that.
Right.
It's just like the Greeks sitting here saying, you all bow us because we go way back.
In addition, what came with this, or what was part of this, was vapor phase epitaxy. And again, this is, without vapor phase epitaxy, we would not have this wonderful world of 3-5 optoelectronic devices in the optoelectronics industry as we know it today. So those were, from my perspective, really what has the key developments. They weren't the only developments, but were they really the seminal developments that really changed the inflection point for how the world was progressing to really get us where we are today with respect to the photonic integrated circuit. If you look, the optical communications industry is really been continuing, and you can trace this curve back for, give me, my diode laser is acting up. But you can trace this back, but it's really been on a exponential growth curve, and it's been oscillating between 50 to 100% per year compounded annual growth rate. And this bandwidth demand really is compelling from both what it creates from an application standpoint, but also what it demands of the technology. And it's not just the bandwidth demand, but it's the economics that go with it. Because while the bandwidth demand is scaling, the economics are not. So specifically, if you look, you see that you go from a 4-minute song to a 45-minute TV download to a 2-hour movie to a 2-hour HD movie, and you see the associated size associated with this, but you see that the pricing that goes with that. So the pricing is scaling by a factor of 3, and we're increasing by 1,000x relative to the total size of the information. And so
you're saying that's a brutal battle with it.
It's a brutal battle, and it's relentless, and it's why that our belief is that the only way that you're going to continue down this progression is by being on the semiconductor curve, and specifically being on the integration curve. And it's not just about photonics, it's about electronics, and integrating both of those and driving down that curve. That's the only way I think that you can continue down that type of exponential progression. So for telecommunications, the metrics that really matter are cost per bit or power per bit. And this really goes to cost implications from CapEx and OpEx, capacity per chip. And this really goes to how well I can deploy and easily I can deploy these, what density I can deploy, and reliability. And the maximum capacity I can put down my medium or my fiber, which is really spectral efficiency. And what you can't do is you can't solve one of these quadrants and fulfill all of the requirements for the scaling. You have to simultaneously fulfill all three. And that's where this intersection is where we really believe that photonic integration really solves a unique problem for the network. So traditional transport, optical transport, for dense wavelength division multiplexing typically occurred with a discrete diode laser, modulator, wave lockers, receive photodetectors, and you had a discrete set of components. And what you did to increase your capacity was you simply added wavelengths into your system and put those increased number of wavelengths down to fiber. This scaled to an extent, but effectively at some point it falls apart because you're literally just building a massive amount of gold boxes here that you have to integrate into your system. And it doesn't work from a cost point of view, it doesn't work from a density point of view, it doesn't work from a power point of view. So what we've done at Infinera is transform that whole array of gold boxes into two integrated chips. And the first product that we have out is a 100 gigabit transmit and a 100 gigabit receive photonic integrated circuit. And the benefits of these are that we can drastically reduce the space and power requirements. We have higher reliability. Most of the reliability issues that occur with optical components are not in the chip, they're in the package. So the fact that I can eliminate 50 packages, say, drastically improve my reliability of my system. Because I am now deploying 100 gigabits instead of an individual wavelength, I have all that capacity ready as soon as it's needed. So I am much more flexible in terms of being able to provide services. I can also now, because I have, when I integrate these devices, I have a low-cost way of getting things into the electronic domain, where in that case now I can integrate electronic switching. And again, now I can do a whole set of electronic processing that I can't do if I'm trying to do an all-optical network. Right? Lastly, I can integrate this electronic access into my network management, and I can really change the rules in terms of how I build networks. So I wind up with a sea of capacity, effectively, that I can switch onto very different data streams and deploy that in a way that allows very rapid provisioning of services. And I can make it basically transparent to the customer, so that all they see is that I have a new service that I need to add. They don't see this pool of bandwidth that sits underneath it because I electronically switch it onto this higher capacity optics. And this is the system that we actually sell. So we don't sell optical components. We sell a full transport dense WDM system. So a little bit of the history here. As I showed earlier, these are commercial transmit devices deployed in the network. And the first devices that were deployed in the fiber network occurred around 1976, 1977. These were LEDs. And what you find is that these discrete devices, people scaled to increase their bandwidth, and they eventually went from LEDs to diode lasers. However, after you got to a little bit over a gigabit, you started to run out of gas from the ability to have a discrete individual device attain these speeds. So the question was, how do we continue that scaling? So if you look around, people started to look to integration. And one of the early examples of optoelectronic integration was some of the work and products that came out of IBM. And this is work that actually Milton directly contributed to, was how to make 1 and 2.5 gigabit OEICs. And this was in the mid-90s. And if you look, then you can see that is one of the things that I think naturally seeded some of the next progression, which was to take these transmit devices and start to integrate more functions onto a single chip. And specifically now what you wind up with is a laser integrated with a modulator on a single chip, which again allows you more flexibility in your device design. So now I can go longer distances. But again, what happened was these devices kind of ran out of gas around 10 gigabits per second. And literally the industry stayed at 10 gigabits per second for about 10 years for the capacity that was deployed on a single chip. And that was until in 2004, we developed devices that were 100 gigabits per chip, which were 10 wavelengths at 10 gigabits per second. What this entailed is moving from discrete devices to 2 elements per device to 4 elements, which was kind of the state of the art of kind of small scale integration in photonics, to over 51 elements on a single device. And this is a diagram of that chip you saw earlier. It's got an array of tunable lasers. It has an array of 10 gigabit modulators. It's got an array of variable optical attenuators to flatten or skew the power. It's got an array of monitor diodes on the back. And then it's got an optical multiplexer all integrated on one chip. This then gets coupled to a fiber, and so then it will get transmitted down the network. And then it gets received to a demultiplexer, and then 10 high-speed 10 gigabit photodetectors. And what you see here, again, these are the laser spectrum, 10 different lasers. These are the filter spectra kind of superimposed on it. So you see these have to all line up to get low-loss transmission. And then here's the receive side filter spectra. And you see that you need good isolation between each of these bands to be able to isolate the signals. And as I talked about the device reliability, we actually have now over 300 million hours in the field without a failure. This corresponds to 3 fit. This is actually more reliable than the single submarine pump lasers that are deployed under the ocean now. So the chip reliability is extremely good, and now I've eliminated 50 packages from my system.
Where is silicon falling this typically?
From a reliability standpoint, the fit rate is there's standard rules for calculating fit rate, and it depends upon many different parameters, including how many gates, for example. So you have to kind of compare, I think, apples to apples on that. But I think 3 fit would be a very low number for an IC. But but it's not necessarily a fair comparison because I think you have much larger gate counts. What we've proceeded to do is we've introduced the next generation photonic integrated circuit now, where we've introduced SOAs onto the device. And these devices have been deployed in the field. The SOA has got something like 13 dB of gain. This allows us a lot more output power. And the consequence of this is now we can attack submarine routes. So we literally have devices that close, and these are real deployments where customers are carrying live traffic over 6,000 kilometers across the ocean. And what we've literally been able to do is compete with these integrated devices with discrete devices on a par performance. So we don't suffer any performance penalty from having this integration. The net result of this, which we're very proud of, is that we are now the #2 worldwide market share company for long-haul dense WDM. We are second only to Huawei in China. If you actually take out Huawei's Chinese sales are actually tied for number one.
Why are they so big? What makes them so big?
The vast majority of their market is in China.
It's cheap.
Yes, yes, they're a private company, so they don't have to report their financials. And I think it's there's a lot of you don't know because you don't see them, but there's a lot of speculation that they actually sell most of their equipment at a loss, at least in this market. All right, and I think the philosophy is literally that it's the 100-year plan, right? With the idea that if you invest for 100 years, you will own the market, right? If you look North America only, we're number one share with 39%. And the next closest person is about a factor of 2 away. Right?
Well, Fred, then if you look at Alcatel, Lucent, and all that, you say basically it's the demise of Bell Labs and the Bell system.
In this market segment, right? They do other things, but and it's a fragmented market. But I think from an area where they were very well known of being leaders for a long time, we do not see their presence. All right. And while all this was happening, while we were out making 100 gigabit integrated devices happen, there was a lot of good work being done here by Milton and his group. And what you saw was that they were taking devices from 100 gigabits all the way up to 700 gigabits for indium phosphide HBTs. And what you find in the network is there's a couple factors that drive what happens in the network. One is you have to have the demand. I think we talked earlier, the demand is clearly there. And then what you worry about is, where's my bottleneck? And what this work clearly indicates is that the electronics isn't going to be the bottleneck. So when we look at this, we say, okay, what are we going to go do next? And how are we going to attack this? Because the electronics clearly is not going to be the bottleneck, so we have to go and scale the photonics again. Right? So if I take this same curve that we talked about earlier, and so here's a 100 gigabit PIC, well, all of a sudden now, Milton's indium phosphide HBTs are racing up there, so now we're going to have the optics being back to the bottleneck again. So what we've been working on for the last few years is, again, how do we continue to climb this curve? And specifically, we've worked on developing 10 by 40 gigabit devices that actually use coherent phase modulation. And that's what we've been developing for the last few years, and that's what I'll talk about next. What we've done to do this is we've had to reach new levels of integration. So before where we've integrated something like 50 devices, we're now up at 450 devices integrated onto a single chip to achieve these kinds of devices. And why do you have to integrate so many devices? Well, what really drives this is that if you look at on-off keying, you really wind up with a small number of components, a laser, a modulator, a detector, and that continues to scale as you scale the data rate as long as you're doing NRZ on-off keying. However, when you go to 40 gigabit, on-off keying NRZ falls apart. You're not able to get the same types of transmission distances. So you have to go to these more complicated phase modulated schemes. And when you do that, you wind up with literally more than 4x the number of components on a per gigabit basis. So this is a problem that just naturally begs to use integration to solve it, right? Because I'm scaling more and more components. So these are the PICs that we've developed now. What you see here is a nested Mach-Zehnder structure, and I'll show this in a little bit detail in the next slide. But it literally there's two interleaved polarizations. So we take a DFB and we split it, one into something that we're going to rotate the polarization off the chip to make a TM polarized signal, and another one where we're going to take and follow the red all the way through. And that's going to stay TE, and then we combine them into a polarization beam combiner. So now we have a set of TM and TE that are going to propagate down the fiber. We have AWGs, we have SOAs, we have 10 tunable lasers, and again we have monitor pins. And when you look at this, this is kind of a simplified structure to make it easier to read, but these are really circuitous layouts. So we do a lot of snaking around because the area is so valuable. We can't afford just to do a linear layout. So really packing in the high density here is really key. So these are some results for a 400 gigabit device. So you see all 10 lasers. You see the individual modulators have bandwidth of over 15 gigabits apiece. And you see the laser line width is a megahertz in this case, which is more than sufficient at this data rate. And you see the 10-channel spectrum. The key was the development of these phase modulators here. And when I say a nested modulator, what I literally mean is you come in and you split into a super Mach sender, and then you have two individual Mach sender modulators, and this actually should come back and combine. So I've got a super Mach sender and two sub Mach senders. So I have 40 modulators per chip. And so how do you do that? Well, it's really key to have the manufacturing capability to be able to do that, and that's what you see here. Right, 40 nested Mach sender modulators, all from a single chip. And then these are the eye diagrams. And how do you get a 400 gigabit PIC? Well, you have 10 channels, 2 polarizations, and now because I'm doing quadrature phase modulation, I've got an in phase and a quadrature phase, so rotated by 90 degrees, right? And each of these running at a baud rate of 11.4 gigasamples per second. So that gives me 456 gigabits per second. And then this is the package that goes with that. You see that these are hybrid packages. This is a high-speed modulator that couples to each of those 40 devices. Here's the PIC. There's 2 fiber couplings in here. And we have a Asic that sets all the controls, because there's a lot of control elements on this PIC that I haven't shown. And then there's the 2 fiber couplings here that come out of the package. There's over 1,000 IOs in this package, and over 17 feet of gold wire bonds. So.
What type of yield you have to do? Yield?
Yield? We don't talk exact yields, but I would say the yields that we achieve on our commercial packages are better than the team primarily came out of AT&T, are better than any discrete package that they've ever produced, even for the integrated package. So, so there really isn't a yield hit at all from a package level. Right. If you look now, we've achieved now these 400 gigabit PICs, and this is what we're literally in process of commercializing and should get deployed in the next 2 years or so. There's a receive side of this that I haven't shown, but it's a coherent PIC with 10 lasers on it as well for the local oscillators. And what this format actually gives us belief is that this is 10 channels at 40 gigabits, but this is only 10 gigasamples per second.
Did I understand you clearly that you're doing in the optical domain the same thing that people do in the electrical domain with detecting and phase shifting and everything?
Just like in radio, yes.
Right. So you're not just using the amplitude, you're using...
It's all phase.
Yeah.
It's all phase.
Paradigm receiver?
Yeah.
Yes. Well, yes. And what has helped enable that is, if you look, people have talked about coherent for a long time, but the problem is that the requirements on the local oscillator, back to in the 70s, because you have to really minimize how much phase noise you have. And what has developed are high-speed A to Ds. And basically what you can do is you can do a linear transformation by sampling multiple times during the bit and comparing that to the previous bit. And that linear transformation can actually allow you to subtract out the phase noise, so it reduces the requirements on the optical local oscillator. So you now can basically have a poor laser effectively that allows you to still do the coherent processing and modulation. Right. And when I say poor laser, it's a megahertz, which is still pretty darn good, right? so we've got 400 gigabit devices, but we believe that these devices are pretty amenable to scaling, at least to 40 channels and at least to 40 gigabaud. And if you do that, you wind up with devices that can go, to 1 terabyte, 2 terabytes, and 4 terabytes. And we believe that that can happen, on a progression of every 3 years or so. So in Milton, this has been a wonderful body of work, but I think now the booger's on your finger.
That $299 that you showed, that cost, so with this kind of extrapolation, where does that cost then go?
If you look, nominally people are expecting for every 4x increase in bandwidth, only a 2.5x increase in cost, and they're seeing, generations go every, 4 to 5 years typically, right, of what's deployed in the network. So you can kind of do the math on that. Right?
When it gets that good, why don't they pay more?
In terms of so what they want is you want instead of TV, you want HDTV. Yeah. Instead of HDTV, then you want 3D HDTV. Right? What's actually amazing, and I pulled the slide here, is that if you look, HD is just kind of an intermediate standard. There's 2 more levels of standard that have already been defined for HDTV, and then there's 3D on top of that. When you get to that, the bandwidth requirements are something like on the order of 10 gigabits per channel, right? Is what you wind up with. So in the home, right? Not in the metro, right? So Milton, I think this is yes, yeah.
So does the last mile become like a big choke point here?
Well, I think it becomes a potential choke point, right? And there's architectures that people are now talking about, right? So you see, this is why a lot of this FiOS is being deployed. There's other architectures that people are now looking at where they're actually looking at coherent, actually in the home effectively. And it's a way to, how do you deal with the whole broadcast select? Yes, I think it becomes a choke point, and you look at what other architectures or solutions you could have here. There's another way to think about this, however, which is what functionality am I integrating into my chips? If you look, this is that same functions per chip versus time, and you kind of see what has been integrated. So you have the LED, you have a laser, you have a tunable laser, and then you add a VOA, a photodetector, an AWG, and SOA. What we've now added are things that include phase adjusters, multi-mode interference combiners, optical bit delays, optical hybrids, polarization beam splitters. So I didn't show it, but we can actually rotate and combine the polarization on the chip. And we can also do polarizers on the chip as well. So from an optical suite of elements, we thought, wow, we're in pretty good shape here. We've got the full suite. And then as we were doing this, as we're going through this, lo and behold, gee, we don't have the full suite. So comes the light-emitting transistor. And this is something that I think is been a very important advance. If you look, it really opens up new possibilities, and partly new possibilities from many different aspects. In one aspect, if I just go back for a second, one of the things, if you look at these circuits, is they tend to look a lot like analog Asics, right? And they look like analog Asics because I can't just make a whole block of MZM modulators and get a functionality after it. I have to kind of combine a kind of unique string of these things to obtain a functionality out of it. So one of the things that people I think have struggled with relative to photonic integration is how do I really have a digital photonic integration where I can really have a repeatable building block that I now utilize. And I think one of the things that, in addition to many of the things that Nick talked about earlier, that is really interesting about these devices is I really have an element now that can truly be a digital building block because I have both the laser and the transistor in one device. And I think that could really open up a whole new realm of what a large-scale photonic integrated circuit is, in addition to complementing how do you continue these progressions? How do you continue to drive up the speed curve? How do you continue to get new kinds of device performance that you can't achieve with a conventional device? And that's where I think if you look, the transistor laser, which followed the light-emitting transistor, really offers new physics, right? And this is a paper that recently was published. Really, we're looking not just from Kirchhoff's law of charge conservation, but making sure that you're taking account for what's happening with the photons in the chip. And I think truly now you're talking about a whole different set of physics, and the question is really, how do you exploit that?
Hey, Fred, go back to your other slide for just a second.
Sure.
Because I just want to mention to the others, I'm sorry I didn't show you slides, but see that bottom one there, you see collector characteristics, then you see compression. Why anyone would want to argue with Milton about that is sort of stupid. Well, I mean, it's thanks.
Sure.
I don't argue with myself.
So in conclusion, the discovery of the transistor really changed the world forever. And it's responsible in many, many ways for the world as we know it today. I think another inflection point was the invention of the visible laser and the demonstration of the viability of the 3-5 alloy. The other comment I would say is large-scale photonic integrated circuits are commercial reality, and its impact are only going to grow from here. And that the work that Milton has done on HBTs, OIC integration, and on the transistor laser with Nick, I think has and I think will continue to have a great impact on the fields of electronics and photonics. And then the last thing that I would echo is there's still much, much more work to do. So thank you for all of the building blocks that you've helped provide, and I look forward to working in the industry with you for a lot longer time in the future. So.
Thanks.